Welcome to our train data. Today I wanted to talk about the 4 moments of a distribution. And the language of moments is really taken from physics, where they talk about like the first moment being angular momentum or whatever it is. In statistics, the 4 moments refer to the center of a distribution, the spread of a distribution, the skewness of a distribution, and then the kurtosis of a distribution. So the first two are things that people are more familiar with than the last two, but we'll get into it briefly in like an introduction video. So we're going to look at data Mtcars, and specifically we're going to look at the weight variable, meaning the weight of the engines. And we can use the mean and the median function in order to get an idea about what the center of that distribution is. And sometimes you can also think about mode as being a measure of center in certain rare cases. If you have like zeros and ones are overwhelming and zero, like you might in some cases kind of think about mode as being center, but really it's median or mean. So here we have the mean 3.2, the median 3.3. The mean is less than the median, which tells us that the distribution here is at least a little bit left skewed. So here I'm going to graph it. I'm using geom v-line layer to create black vertical lines for the mean, or one vertical line for the mean and one gray line for the median. And here we see that the mean is less than the median. So the distribution of the weight of the engines is a little bit left skewed. So this is important when the data is really skewed. For example, when talking about housing prices, the super rich buy very expensive houses, and the mean house price would be much higher than what the average American would be buying. So to think about what an average person might buy, the median is a better measure of center, and that's the statistic that's usually reported. Now, the second moment is the spread of a distribution. I'll run this graph first. Well, there's 2 lines here for black and 2 lines for gray. And the black lines here represent the standard deviation in this data set, and the gray lines represent the interquartile range. Now the standard deviation you can call using the SD function. SD Mtcars $weight gives me the standard deviation of the weight of the engines. That's 0.978. Now remember that the standard deviation is really the square root of the variance, 0.978. Here we go, it evaluates to the same. And the variance is calculated as you take Mtcars weight for every weight observation, and you subtract the mean for every observation, and you square that total, and then you add up all those squares, and then you divide by the number of observations, and here we go. So there's the variance, 0.97, and to turn that again into the scale of the original data, you take the square root, 0.978, and that's the same as the standard deviation that we evaluated at the top. Now, what's the way to think about this? If you want to see how different the weights are from each other, you take how spread out the weights are of the engines from the center, you take every weight and you subtract the average. But you can't just add all that up, because you would end up with 0. So you have to square it first before you add it up. And then you divide by the number of weights in order to get that average. And then to turn it back onto the original scale, you take the square root because you had done the squaring beforehand. So here you do the squaring because you're subtracting the average from each observation. You have to square it so it doesn't add up to 0 as you add it up. And then you subtract by the number of cars, and then you take the square root to put it back on the original scale. So that's the way to think about it. One thing that's also interesting is you take -1 here. That turns this from being the sample standard deviation into the population standard deviation. If you were coding in Python, actually, it doesn't do this -1, which is called Bessel's correction. It actually just reports the sample standard deviation and not the population standard deviation. But R, I think, is a little bit more geared for doing like descriptive and inferential statistics both. And so it sort of has all of this implied under the hood of this SD function. And so by deconstructing this, you actually start to see an important difference, because unless you did Bessel's correction, it wouldn't add up to the standard deviation that you get here. So this is the spread of a distribution. And the last two that I'll cover super briefly will be the skewness and the kurtosis. Now, the skewness, you see, I'm taking each weight variable and subtracting by the mean, but here I'm actually doing a cube. And then I'm doing something a little bit more complicated in the denominator of this equation by multiplying by the number of observations and then the standard deviation cubed. And the kurtosis, I'm also doing the same, except I'm taking this to the 4th power and subtracting 3 at the end. And there's more than one possible equation for skewness and kurtosis here, but these are kind of the classical, most theoretical equations, and so I'm including them here in like the introduction. Now, the skewness of a distribution is like how sloped it is to the left or the right, like we were talking about with the center and the spread. And the kurtosis is actually a measure of how tailed the distribution is, how thick it is on the left and on the right side. But you can also think about it as the peakness of the distribution, because those two things are kind of the same. You know, when the distribution has super thick tails, it's going to have a more narrow peak. And those are also ways of understanding how much these distributions would deviate from a normal distribution.